But actually, I don't really think of reinforcement learning as something philosophical. I think of it as something really pragmatic. I view it as like a way to model the world so that we can solve practical problems. And it's a really useful model because it has a lot of strengths in this respect. It captures a lot of these key elements of you have to make decision making, you have to make decisions, you face uncertainty, you want to reason about expected payoffs. All of these things are captured there, and that makes it a really useful model, a pragmatic model for for solving these kind of problems in your actual life.
Hello everyone, my name is Mukul and this is the Deep Neural Notebooks podcast. This is the 7th episode of the podcast where I interview Dr. Shimon Whiteson. Shimon sir is a computer science professor at the University of Oxford, where he leads the Whiteson Research Lab. He's also a data scientist at Waymo, which was formerly the Google self-driving car project. His research interest includes reinforcement learning, multi-agent cooperative reinforcement learning to be precise. And so this episode is all in the context of reinforcement learning. We talk about his journey, how he got started with machine learning and reinforcement learning. I ask him about his thoughts on the state of reinforcement learning, about how the field has progressed over the years, and why it has become much more popular in the last couple of years. We also talk about his research at Waymo, about recent projects coming out from his lab, and about the future and scope of telepresence robots, one of which was developed under his guidance. I also ask him about his thoughts on the reward hypothesis in the context of RL and philosophy. In the end, he also shares some advice for people who are starting out with reinforcement learning. Timestamps to different segments of the conversation will be in a pinned comment of this video, so if you want, you can skip ahead to whichever part you like. If you like the episode, please support the channel by leaving a thumbs up or a 5-star rating depending on the streaming platform. Thank you.
Great. Hello, Shimon sir. How are you? How are things there? Where are you located right now?
I'm at my home in Oxford, in the UK.
How are things there? As far as the pandemic is concerned.
It's a pretty unusual time, obviously.
Right.
Yeah, I mean, Oxford has been affected just like anywhere else by the coronavirus. So I've been working from home for about 6 weeks. My kids are no longer going to school, so we're just focused on trying to stay healthy and safe, and juggling work and childcare. So it's a pretty unusual time.
It looks like it's going to be extended in the UK for till about June. I think the Prime Minister said so.
There's some discussion about reopening the schools at the beginning of June. I don't know how realistic that is. Well, we'll see.
Right. So has it affected your work routine in any way? Maybe have you had difficulty in being productive during that time?
Yeah, well, so first of all, I've been sick for the past 3 weeks, and I had a lot of symptoms which matched the coronavirus, but I actually had a test, and the test was negative. But the test is also not entirely reliable, so that doesn't really settle anything. Yeah, and so in addition to being sick, the fact that my kids are not in school has had a big effect on my productivity. So I'm only working part-time because it's a lot of juggling.
Right. So I'd like to start with talking about your journey, how you got started with computers and data science. And I think you did your bachelor's in English and computer science at the Rice University. So were you always interested in computer science, or how did that sort of start off?
Yeah, so I was exposed to computers at quite a young age. I actually come from a family of computer scientists. So my mom was a computer scientist and my dad was an engineer who did a lot of computer programming. And both of my older brothers have degrees in computer science. So I was exposed to computers from quite a young age. The first computer program I wrote was when I was 5 years old. My brother taught me to program in BASIC. And so it was always, I mean, the whole time I was a kid, it was something that interested me intellectually. It was like an academic subject that I was always attracted to. So I had a fair amount of programming experience by the time I started at Rice. And I knew I wanted to study computer science. And when I was at university, that conviction was confirmed because it just seemed like the stuff we were doing in computer science was more interesting than what a lot of my friends studying other subjects were doing. Um, a lot of people studying things like medicine and biology, it seemed like they were just being asked to learn a bunch of facts and regurgitate them. Whereas in computer science, we was always about problem solving. Um, so to me, that just made it so much more interesting and fun. Of course, it was also very frustrating at times, as anyone who's tried to write a computer program knows. But yeah, the challenge was addictive.
Right. So do you remember your first computer science project?
So when I was 5, I remember writing a computer program, like graphical programs that would like paint different shapes on the screen and have like simple animations. It's amazing what you could do just with BASIC on a Commodore 64.
Right.
Academically, gosh, I don't remember. At Rice, I remember doing projects. We had to make a compiler. We made a browser. We did some projects with genetic algorithms. I think Rice is where I first started programming in Java and where I was first exposed to functional programming.
Right. So what did machine learning look like back then, and were you sort of getting interested in that as well, or was it just plain computer science, problem solving, programming?
So as an undergraduate, I was only very dim aware of machine learning as a concept. I was interested in artificial intelligence. I had been interested in it for a long time, and I think artificial intelligence is one of those subjects that it has an appeal to outsiders. There's something kind of intriguing about it. So I think at the time I was an outsider, and so it was intriguing to me. But I didn't really have any academic exposure to it. So when I was at Rice, I took only one course on artificial intelligence, and it was like a typical introductory course using Russell and Norvig. The focus was not on machine learning. It wasn't really until I was a graduate student that I had any serious exposure to machine learning, or that I started to focus on it as a subject for research.
Right. So then you went on to do your PhD at the University of Texas, Austin. And so that was where you sort of pursued machine learning. So how did that transition happen for you? Because you said till your graduation, you were not quite aware of how things were in the machine learning space. But then how did that transition happen?
Yeah, so one of the reasons why I chose to go to UT Austin was because it had a large department, and a department that was strong in many areas, because I was really unsure what I wanted to study. I knew I wanted to do more with computer science, but I wasn't even sure I wanted to do AI. I thought I wanted to do AI, but since I'd only had that one course, I didn't really know. I was also interested in theory. Actually, the courses I enjoyed the most as an undergraduate were things like algorithms and complexity, much more theoretical subjects. But I was just fascinated by AI, and I wanted to study it more. So that was one reason to choose that department, was just to keep my options open. And another reason was because I wanted to work with Risto Mikulainen, who's a professor at UT Austin, who actually his focus was not on machine learning. His focus was on evolutionary algorithms, and in particular neuroevolution. So that's a concept I was exposed to there as a graduate student. And that ended up being kind of a gateway to machine learning, because we were using neuroevolutionary algorithms to solve a lot of different kind of problems, but in particular control problems like a RoboCup simulated soccer, and sub problems thereof, like keep away is a standard benchmark problem in RoboCup, where like 3 agents try to keep the ball away from 2 agents that are trying to take it away. And I mean, at the time, I wasn't even really familiar with the term reinforcement learning, but we were just applying neuroevolutionary algorithms to these problems. At a certain point, it became apparent that what we were doing was a form of reinforcement learning, and that there were all these families of other algorithms we needed to compare against. And that became kind of my entry point to reinforcement learning. And it just so happened, when I was already a graduate student there, that the department recruited Peter Stone to join the faculty. And he, of course, was like a wizard at RoboCup. He had won the RoboCup Simulation League like year after year as a graduate student. And also he had a more traditional background in reinforcement learning. I really hit it off with him and started collaborating with him. And that led to me doing a PhD thesis at kind of the intersection of neuroevolution and reinforcement learning. And that kind of completed my transition to reinforcement learning as a field of research.
Right. So you mentioned about RoboCup. So was it in simulations during that time, or was it out in the open?
So I only ever worked on a RoboCup simulation, and actually mostly just on Keep Away. But Peter Stone, I mean, he was and still is involved in RoboCup pretty much in all forms. And after coming to UT, he started a robotics lab, and so a lot of my my peers, my like fellow advisees of Peter, they were working with physical robots. At the time, there was a big focus on the Sony Aibo, the robot dogs, and now I think they're doing humanoids.
Right, right. So in particular, what did your PhD work focus on at the intersection of neuroevolution and reinforcement learning or machine learning?
Yeah, reinforcement learning. Yeah, so so at the time in Risso's lab, there was a lot of emphasis on developing neuroevolutionary algorithms that don't just learn the weights of a neural network, but also learn its topology. So decide like what the nodes should be and how they should be connected to each other. That's part of the evolutionary process. But then, you know, during the lifetime of any particular neural network, the weights were typically fixed. So the main idea behind the PhD thesis was that, like, in addition to evolution, these agents could also learn during their lifetime. So the weights, instead of just being fixed and, you know, directly mapping states to actions, the output of the network could be interpreted as a value function, and those value function estimates could be updated and improved during the agent's lifetime using reinforcement learning algorithms like Q-learning. So that, you know, then this leads to a lot of interesting interactions between evolution and learning. There's something called the Baldwin effect, where like evolution and learning kind of interact synergistically. And you can also do things that might not be biologically correct, like Lamarckian evolution. After you've done this learning, you can actually like write the phenotypic changes back into the genotype so that they're passed on to their descendants, which is something that wouldn't happen biologically. But you're free to do it on the computer, and you know, you can then compare it to Darwinian evolution. So yeah, that was it was kind of developing algorithms at the intersection of those two, and trying to get the best of both worlds.
Right. And how prevalent the neural networks back then? I mean, I think the optimization and the backpropagation things, they came out a little later. Around 2011 and 2012, they became more ubiquitous. But 2004 and 2005, I mean, what did neural networks look like back then?
Yeah, so this was pre-deep learning, so neural networks were a lot smaller, and I mean they were one sort of typical way to represent a value function in reinforcement learning, but they definitely were not the dominant way. And in fact, they were considered quite problematic. So the conventional wisdom at the time was that doing reinforcement learning, like traditional reinforcement learning with temporal difference methods on neural networks was unstable. So the empirical success that existed, which was limited, was often not with neural networks, because it was easier to get the linear function approximators working, and there was much more emphasis on tabular representations, because that was all that was sort of that worked reliably and that was amenable to study. And that was one of the motivations for the project was, you know, if we wanted to stabilize reinforcement learning with neural networks, then we needed to have the right representations. We needed to solve this representation learning problem. And these neuroevolutionary methods that discover the topology of the neural network, that was what they promised to do. So in a sense, it was kind of like foreshadowing what happened with deep learning and reinforcement learning, because deep learning came along and addressed the representation learning problem, so that neural networks could become powerful function approximators for reinforcement. They just ended up in a way than with the neuroevolutionary methods that we were trying to get working.
Right. So then you went on to become a professor at the University of Amsterdam, and then after 8 or 9 years, I think you joined Oxford. So how has your research shaped over the years? How has it changed? And are you still working on the things that you started off with, or has it taken a different direction?
Yeah, I mean, it has meandered over time. I mean, I think I'm a bit of a dabbler, so I definitely like switch my emphasis every few years. When I went to Amsterdam, I got a lot more involved in multi-agent stuff. So there was an effort already underway there to do a multi-agent planning. So that was started by Nikos Vlasis, who had actually left by the time I arrived. I was kind of his replacement. But Frans Oliehoek, who was his PhD student, he and I started collaborating when I went to Amsterdam, and he's now, one of my main collaborators, one of the people I've collaborated with the most over the years. So we did a lot of work on multi-agent planning. And also in Amsterdam, there was a very strong group on information retrieval led by Martin de Rijke. And they were really looking for, machine learning tools that could improve information retrieval. And I started to realize that it was basically a reinforcement learning problem. Maybe not a full reinforcement learning problem, but like a bandit or a contextual bandit problem. So we had a big collaboration on that topic also. Actually, when I was in Amsterdam, I wasn't doing that much of what you would strictly call reinforcement learning. So the information retrieval work was closer to bandits than to a full reinforcement learning problem. And the multi-agent work was mostly planning, not learning. So it actually wasn't until I came to Oxford, which was around the time that the deep learning revolution was transforming reinforcement learning, that I really got back into reinforcement learning. And that was actually primarily student-driven. So people often mistakenly assume that I have complete control over my research agenda and that I make thought out strategic decisions about what to focus on. But actually, I'm quite limited by what the students want to do. And all the students wanted to do deep reinforcement learning. So that's what I started doing. And, fortunately, it's a very rich and rewarding topic to work on. But I couldn't have avoided it if I wanted to.
Okay. So you've been in the field since around 2004, 2005. And it seems like the field reinforcement learning has gained quite a lot of popularity in the last 4 or 5 years. So what could the reasons be for this, apart from the rise of deep learning and networks getting deeper and more competition being easily accessible to everyone?
Yeah, I mean, I think if you wanted to put together a causal chain, I would say it probably starts with the availability of much better compute. It starts with advances in high performance computing that enabled all these advances in deep learning, and these advances in deep learning have totally transformed reinforcement learning. Many of the other changes in the field I would describe as effects rather than causes. So the field has gotten much bigger. There's way more people working on it. There's been a lot of algorithmic innovation, but all of that has come because of the intense interest around the subject as a result of deep learning.
Right. And how much does RL depend on deep learning in that sense? Because ever since the onset of deep learning, feels like computer vision and natural language processing have almost completely shifted to these paradigms, and now they're only using the traditional approaches to sort of improve upon the learning procedures. But how much does deep learning influence the research in reinforcement learning?
I think it influences it a lot. I think without deep learning, reinforcement learning would still be kind of a backwater. It would still be quite a niche area, and rightly so, because the algorithms just wouldn't be robust or reliable enough to really offer benefits in many applications. So, for most of the large-scale challenges and applications that we're interested in, deep learning is an essential ingredient in reinforcement learning. And I think the main reason for that is that it sweeps away a lot of the representational challenges that otherwise just become a key bottleneck to progress. It's hard to represent things like value functions and policies. You need good representations, especially if you want to stabilize, the algorithms that we rely on for learning. And without an automatic mechanism for learning those representations, it's hard to make progress beyond simple problems. So, I'm someone who's like more of a user than an innovator in deep learning itself. So my research is not about like designing new architectures for neural networks, but all the advances in deep learning that happen, we steal them and use them in reinforcement learning. And I view it as a useful tool because it sweeps away that bottleneck. And then it allows us to then move on to some of the interesting challenges that we've been thinking about for years, things like exploration, which you can study, in a theoretical way in a grid world and do lots of interesting research about, but it's all kind of hypothetical. Until you solve these more proximal representational problems, it doesn't become the bottleneck in the applications. So deep learning is great because it means we can actually we can actually make practical progress on things like exploration because the more proximal issues have disappeared. That being said, I think deep learning is something where not every nail needs this hammer, and we should, when we're doing research, we should always remember to try simple baselines, to try doing reinforcement learning without deep neural networks and compare the performance. And now that I'm also working on the industrial side, that's really underscored for me the fact that oftentimes the most practical solution is a very simple one. So we don't always need to have a big neural network involved.
Right. So in a field like reinforcement learning, wherein you can do the exploration and the learning part inside a simulation and then extrapolate that to be used in the real world. So what has the convention been for that, for let's say for robots that are being created and used in the industry? So are they all trained in a simulation environment? And then, is that the convention now, or are they also being sort of trained in the world out there?
So I guess I would say there's kind of three categories. There's just trained in simulation and that's it. That's probably the most common. And if you look at the big splashy empirical successes that reinforcement learning has had, that's what it is. Things like Atari, everything is done in simulation. Then there's sim to real, which is you want to get a control policy for a physical robot. It's too expensive to do all the training on the robot, so you do the training on the simulation, and then you try to deploy on the physical robot. But that can be quite difficult, so that transfer process can fail, and it can fail catastrophically. So there's a lot of interesting research about how to improve your simulator so that it better matches the real world, or how to learn robust policies so that when you do that transfer, you're less likely to have catastrophic failure, or once you're deployed, how can you learn quickly to fix any remedies in the policy that you learned in simulation? And then the third category is just do all the learning in the real world, which I think almost never happens in practice because it's just too expensive and dangerous.
Right. So now you're a chief data scientist at Waymo. And so what are some of the interesting challenges that you're facing in the company? In the work that you're doing at Waymo?
So at Waymo, at least the part of Waymo research in which I'm working, the focus is not actually on reinforcement learning; it's on learning from demonstration. So the key goal of the team that I'm working on is to use machine learning to develop realistic behavior models of the road users that an autonomous vehicle might interact with. So the human drivers, the pedestrians, the cyclists, we need really good models of their behavior in order to have reliable simulation tools. And simulation tools are key to efficiently training and testing an autonomous vehicle. You can't do all your training and testing in the real world. You have to do most of it in simulation, but it's useless unless the simulator is realistic. And the simulator won't be realistic unless it has good models of the other road users that the autonomous vehicle will interact with. So learning good models of those road users is a key challenge. And we're doing that not with reinforcement learning, but with learning from demonstration. So we take, trajectories, data, log data, examples of the humans behaving naturalistically in the real world in traffic situations. And we try to learn from them control policies that both capture and generalize from that behavior in a realistic way.
Predicting the path of a vehicle based on the movements of the pedestrians and other moving objects on the road.
Yeah.
In a simulated environment.
Yeah. We want to populate the simulation with realistic road users, and so we need to learn control policies for those road users from data.
Right. So, what is the demonstration part here? What is this what is this demonstrated to? What part is demonstrated to which entity in the whole learning process?
So learning from demonstration is similar to reinforcement learning in that the goal is to learn a control policy that maps states to actions. The key difference is that in reinforcement learning, you assume you have access to some reward function. So when you try out actions, you get some feedback about how good they are. Whereas in learning from demonstration, you assume you don't know that reward function, or it's too difficult to quantify that reward function. But instead, you have examples from some expert who knows how to perform the task, examples of them doing it. So you have a bunch of state action pairs. In this state, the expert took this action. In that state, the expert took that action. So here, the task is, behave like a human. behave in a socially normative way while driving in traffic. That would be a way to characterize the task. And it's very difficult to write down the reward function for that. Because the nuance there, the unwritten rules of the road that govern the way people interact in the road, it's very difficult to quantify that in a reward function. But we have all these demonstrations. We have logs. We can see the way that people have behaved in traffic, and we can interpret those as demonstrations, and then we can learn to imitate the demonstrated behavior.
Okay. So one of your key interests has been multi-agent reinforcement learning, cooperative multi-agent reinforcement learning, and there's a lot of work coming out from your lab on this field. So could you talk about the motivation behind building such multi-agent systems or developing models for such systems for agents that can collaborate and sort of optimize some tasks? So what are some of the applications for this? And what's the key motivation behind building something like this?
Yeah, sure. So multi-agent RL is I think a key topic because it allows us to move beyond one of the unrealistic limiting assumptions of the reinforcement learning framework, which is that the agent is the only agent in the world. So in the RL framework, there's just an agent and an environment. But of course, we know that environment in the real world will almost always contain other agents. So we need multi-agent RL because we need to build agents that know how to interact with other agents, whether it's cooperatively or competitively. So I think that's like a key generalization of the framework that we need to capture a lot of the complexity of the real world. So at a high level, there's kind of three kinds of multi-agent RL. There's fully cooperative, all the agents are on the same team working towards a common goal. There's fully competitive, like a zero-sum game, where the agents' interests are diametrically opposed. And then there's the kind of messy, mixed general sum setting where the agents may have overlapping interests, but their interests are different. In an economic situation, we all participate in an economy together. There are mutual benefits to like trading and interacting, but obviously, when I sell you something, I want to get a high price and you want to get a low price. So from a research perspective, my focus has been not entirely, but mostly on the fully cooperative setting. And I like the fully cooperative setting because it's rich enough to capture a lot of the key challenges we have in the real world. There are many real world problems that can be modeled cooperatively. And it doesn't require making a lot of unrealistic assumptions that you typically do have to make to build algorithms in the other settings. So we don't have to assume that the other agents are rational or that they use the same learning algorithm as us. Or if we do make those assumptions are realistic because it's a cooperative setting. So we assume, we know we're able to control the policies of all the agents because they're all on the same team. They're all, a bunch of robots being deployed by the same human actor. In the cooperative setting, there are many real world applications. So you can think about, fleets of autonomous vehicles that are working together, a bunch of drones that need to work together to survey an area or deliver packages. You can think about logistics problems, both on the road and in warehouses and factories. Traffic management. So, for example, if you have an agent controlling the traffic lights at an intersection, it needs to coordinate its behavior with the traffic lights at other intersections. Closely related to that are things like packet routing. It's basically traffic management, but with packets instead of cars. Video games is a very interesting application. We want to have better, more realistic game AI, for humans to play against, and the different AI agents then need to cooperate with each other, or sometimes they need to cooperate with human players. So there are a lot of real world applications in the cooperative setting. The research in my lab has focused mostly on this setting that we call CTDE. So centralized training, decentralized execution. So here the assumption is the problem that we ultimately want to solve is a truly multi-agent problem. And the thing that makes it truly multi-agent is that there's partial observability. So each agent has only a partial view of the world, and each agent's partial view of the world is different. So I see some things and you see other things, and they're not the same. And because of this partial observability, we have a problem that can't be like collapsed into a single agent problem. We can't think of it as like, okay, there's one puppeteer agent that's the only real agent, and he just tells all the other agents what to do. In a fully observable setting, you can think of it that way. But when there's partial observability, you have like a real multi-agent problem where the agents are going to have to make a decision on their own to some degree with only limited information about the world and about what the other agents know. So that's the decentralized execution part. But we make the assumption that the training is centralized. So when we're doing the learning, we're going to be training these agents in a laboratory setting, like in a simulator or in a laboratory where those restrictions that happen in the real world don't exist. So either it's a simulation, so kind of we can do whatever we want, or it's like actual physical robots, but in a laboratory where we can give them extra sensors, so the partial observability they'll have when they deploy won't exist, or we can have them communicate with each other so that there's no communication constraints between them. We can strip away all those constraints during learning. And then the kind of really interesting research question is, how can we exploit that centralization of the training process so as to more efficiently learn a set of control policies that are decentralizable? So once we're done with learning, we need to be able to deploy the policies in the agents such that they can obey those constraints, such that they condition their action only on what's available to them out in the real world. But during learning, they can share parameters, they can share gradients, they can share observations. There are no rules. So this is a special case of what's sometimes called privileged information. So this happens a lot in robotics. You want to deploy the robot, and the robot you deploy needs to be, it can't be too expensive. So you can't put really fancy sensors on it. But when you're in the lab, you can give it fancy sensors. So during training in the laboratory, you have this privileged information. And how do you use this privileged information in order to learn faster? So in the multi-agent setting, we have a special case of this privileged information, which is the agents are free to share everything, even though they wouldn't be in the real world. So, like a trivial example of how to use privileged information is parameter sharing. Each agent, rather than learning its own policy, every agent, we just learn one policy and we copy it into the brains of all the agents. So the experience of one agent is used to update the policy that's also used by another agent. Another thing that you can do is, if you take an actor-critic approach to multi-agent reinforcement learning, you can centralize and share the critic. So in an actor-critic approach to reinforcement learning, the critic is really something that you use only during learning. Once you're done learning, you can throw the critic in the bin, and just the actor will tell you what to do once you're deployed. So anything like that you throw in the bin when you're done learning is a great candidate to be exploited by centralized training. So we can learn a centralized critic that isn't decentralizable at all. Doesn't matter, because we won't need it when we get to the phase where we decentralize. So we've been doing a lot of work about how to maximally exploit this centralization of training.
Right. So are there any specific projects that you could mention that your team has been working on in the last 2-3 years in this regard?
Sure. So we developed both actor-critic approaches and like Q-learning based approaches for this setting. So the actor-critic approaches, I basically already described to you how that works. So it uses a centralized critic and decentralized actors. And there's some other tricks to make the learning more efficient. So in policy gradient methods, the variance of the gradient estimates is kind of usually the central challenge. So we developed something called a counterfactual baseline, which is like a way to reduce the variance of those estimates by having the agents, reason about counterfactual scenarios in which the agents would have selected other actions than the ones that they did in the data. We also developed this algorithm called QMix, which takes more of a Q-learning approach. So it learns a centralized value function, like a joint value function. It maps the state and the actions of all the agents to like an estimate of the value that the shared reward signal will provide. But it does so, this centralized value function is factorized in a way that means that once the value function has been learned, the agents can individually select their actions without having to coordinate with the other agents. So basically, if you had a centralized value function and it wasn't properly factorized, then once you learned this value function, it wouldn't be clear how to act. Even if magically you learned the optimal value function, it wouldn't be clear how the agent should actually act. In order to select the joint action that maximizes this joint value function, you have to solve this combinatorial problem by finding the best joint action in this huge joint action space. And that would require the agents to coordinate with each other. But if you estimate the value function in a way that respects this factorization, then that's not true. The argmax that you need to perform in order to decide how to act can itself be decentralized. So each agent can just select an action according to like its local component of this learned value function. And the resulting joint action would be the same as if you did that joint argmax. So by sort of carefully defining the factorization in the right way, we achieve this decentralizability, which is key to the CTDE setting. So more recently, we had a paper about exploiting common knowledge. So one of the limitations of this setting is that when you get to the execution phase, the decentralization is complete. So that means while you may be able to do whatever you want during training, once you get to the execution phase, the agents cannot communicate with each other at all. And that's quite restrictive. So what we looked at with common knowledge is there a way that the agents can coordinate their behavior even without the ability to communicate with each other at execution time? And it turns out that that is possible because even though the agents cannot communicate with each other, they may share what's called common knowledge. So common knowledge is something that all the agents know, and all the agents know that they know it, and all the agents know that they know that they know it, et cetera, et cetera. So if you make some assumptions about how the world works, you can actually establish common knowledge between the agents. So a simple example is all the agents have partial observability, right? Because it's a truly multi-agent setting. Let's suppose that partial observability comes in the form of a field of view. So every agent can only see like a certain radius around it. But if we assume that within that radius, its observations are reliable, like its perception system is more or less correct within that field of view, and you assume that the agents know each other's fields of view, which is also a reasonable assumption in the cooperative setting, because we can assume, okay, I know what sensors my teammates have. Yes. Then, if two agents can see each other, then they share common knowledge about their location. So I see you because you're in my field of view, and I know that you see me because I know your location from your field of view, and I know what your field of view is, so I can figure out that I'm in your field of view. So then our locations becomes a common knowledge to the two of us. So we developed this algorithm called Mackerel, which tries to exploit this common knowledge.
But what if they're not in each other's field of view and cannot communicate with each other? Would that be helpful? I mean, could that be exploited as well?
Well, so in that case, they don't have common knowledge. At least they don't have common knowledge about their locations. Mm-hmm. So when the agents have common knowledge, then they can make a more coordinated decision because they can condition on this shared information. Mm-hmm. And then there's a really interesting trade-off because you have to decide at what level to coordinate. So, for example, if you coordinate globally, the coordination is better in the sense that the coordination takes every agent into account. But at a global level, the agents may share only very weak common knowledge. Whereas if you take a subset of the agents and say, okay, we're just going to coordinate within that subset, the coordination is weaker because you've only coordinated among the agents in the subset. You haven't coordinated with the agents outside of it. But the coordination that happens within that subset may be much more effective because within that subset, the agents may share much stronger common knowledge and therefore be able to coordinate much more effectively. So that's the trade-off, is deciding at what level to do the coordination. And Mackerel is an algorithm that tries to do that in a hierarchical way. So basically, at the top level of the hierarchy, you can either say, okay, we're going to decide how to act, or we're going to delegate the decision to some subset in the hopes that subset will be able to decide more effectively because that subset will share stronger common knowledge.
Right. So are you, is the team only working on developing such systems, or do you also cater directly to the industry and specific projects, specific implementations for certain applications?
So on the multi-agent side, we're not really looking at industrial applications, but we are quite focused on benchmark problems. So we developed something called SMAC, which is basically takes StarCraft 2 micromanagement and formulates it as a cooperative multi-agent RL benchmark problem. So micromanagement in StarCraft means, like coordinating the positions and the firing patterns of different agents so as to try to like beat a game AI. And there's a bunch of different maps where you have different terrain and different combinations of agents and different types of agents. And, suites of these maps taken together form like an interesting multi-agent RL challenge problem. So we developed this whole software framework called PyModel, which has been open sourced, which you can, connect to SMAC. So you can take our algorithms and algorithms that have been developed by others in the community and apply them to these benchmark problems and, see which algorithms perform the best. So making progress on those benchmark problems has been a key focus of ours. Some of these maps are quite easy. Some of them can be solved only with, the most clever algorithms we've come up with, and some of them we still can't really solve. So, we're kind of focused on making progress on those. Recently, we've also started looking at football. So Google has this new football project. It's kind of related to the RoboCop Simulation League, but it's all been built to play nicely with modern machine learning tools. So we're looking at applying our algorithms to that setting also to sort of expand the breadth of the benchmark problems we look at.
Right. So while looking you up on the internet, I came across the Teresa robot. That was kind of your brainchild. So from your work on, so I'll just tell it for everyone. So the Teresa robot was a telepresence robot that allowed people who were in remote areas to communicate with others, primarily for the elderly. So from your work on Teresa and in light of the current pandemic, are there any insights that you can draw about the scope of semi-autonomous and autonomous agents like these in the society, helping sectors like healthcare, medical institutions, doctors and nurses, or in other parts of the society?
Yeah, so telepresence is a fascinating technology because, it allows you to do the kind of thing that, that we're doing right now and that people are doing so much more of as a result of the pandemic, which is, interact remotely. But it enables you to do it in a more natural way and in a way that facilitates more spontaneous social interaction. So with a telepresence robot, instead of just having a meeting like we're having now at where the people you're going to interact with and the setting is fixed in advance, with a telepresence robot you can do something like mingle at a cocktail party, have spontaneous interactions with people that you just bump into at a party because you're controlling a mobile robot that's attending a physical event. Or similarly, like a doctor can do rounds at a hospital and so on. These are kind of applications that are more natural and easier with something like a telepresence robot than with something like Zoom or Skype. So in the Teresa project, telepresence robots are, like, from a technological perspective, quite simple. It's a simple mobile robot. It uses an ordinary internet connection. There's two-way audio and video. It's quite unremarkable technologically. In the Teresa project, we were trying to take that further by making the robot semi-autonomous. So giving it some social intelligence so it could take over some of the low-level behavior. So, when you're controlling this robot and you're trying to have a conversation with someone, you can be distracted from the conversation because you have to manually do things like maintain an socially appropriate distance from the person. Kind of thing that you would do automatically if you were physically present. Suddenly you have to do it manually, and that's distracting. So we were trying to remove that distraction by giving the robot the social intelligence to do those kind of things automatically. And that was very interesting from a research perspective, and we built, I think, quite a cool proof of concept. But using machine learning to learn social intelligence is quite a nascent field, and I think we have a long way to go before we can do that in a robust enough way to, such that something like that could actually go to market, that you could buy a telepresence robot that is socially intelligent. It's a great application of learning from demonstration. So the sort of the situation where you want to do learning from demonstration rather than reinforcement learning is a situation where the reward function is hard to write down, but the behavior is easy to demonstrate. And this is a perfect example. It's like behave in a socially normative way, any ordinary human can demonstrate that behavior. And you do it effortlessly when you have a conversation with someone. You maintain the right amount of eye contact. You stand in appropriate orientation and position from them. But if I asked you to write down what's the reward function for socially normative interaction at a cocktail party, good luck. So we used a lot of learning from demonstration in the Teresa project, and that's actually where we developed some expertise on the topic, and that led to starting the Latent Logic, which was the spin-out company that I created to commercialize learning from demonstration technology, which led to the acquisition by Waymo.
Right. So, are there any similar robots that you're working on right now? I mean, since the Teresa robot couldn't continue, but are there any other similar projects that you're working on?
So I mean, I'm not a roboticist, so I don't have like a robotics lab, and most of the applications that we're working on are just in simulation, like I mentioned, the StarCraft thing. But I do like to collaborate with roboticists because I think robotics is an important application of reinforcement learning, and I think it's quite an interesting one. But it's one where if you're not an expert in robotics, it's quite difficult to make progress in. So rather than trying to be a roboticist, I like to collaborate with roboticists. And that's what the Teresa project was all about. So I was leading that project, but that project would never have happened if a lot of people with deep expertise in robotics hadn't been involved. Since the Teresa project, I've done some other collaborations with roboticists. So we've collaborated with some roboticists in France to apply some of this robust reinforcement learning algorithms that we've developed to their hexapod robots. So we try to learn control policies that are robust to what we call significant rare events. So something that happens with very low probability, but if it happens, it has a huge effect on your expected return. So it's actually very important when you choose a policy that you take those rare events into account. But it's very hard to do so because if you just train in simulation, those rare events probably won't happen the whole time in training, and you'll just miss them. So we developed some algorithms that try to get around that and learn policies that are robust to those rare events, so that then when you deploy them, the behavior is better. And we did some experiments on these physical hexapod robots where we show, like, okay, if the hexapod breaks a leg, the learned policy is more robust if we use our algorithm than if we take a naive approach. And now I'm actually just starting a collaboration with the Oxford Robotics Institute. So at Oxford, I'm in the computer science department, but next door in the engineering department, there's the information engineering, where there's actually as much or even more machine learning going on there than in the computer science department. And part of that is the Oxford Robotics Institute. It's a world-class institute doing all kinds of robotics. So Ingmar Posner is one of the roboticists there, and I'm collaborating with him now, together with a PhD student in my group. And we're looking at doing things like meta-reinforcement learning or model-based reinforcement learning, but for robotics applications.
Right. So on this intersection of reinforcement learning and robotics, are there any bottlenecks that these fields are facing? For example, I read that for building the Teresa robot, it was difficult to get the hardware together. And usually hardware is a problem currently from porting to software to creating these actual robots. So could you share some of the other bottlenecks that are there?
Yeah, hardware is definitely a big bottleneck, and working with robots is very frustrating because of the hardware limitations. I think probably the software is a lot more advanced than the hardware. Just building robots that work reliably, that don't break every other time you try to use them. Things like battery life, the sensors and manipulators are not nearly as advanced as we'd like them to be. That's one reason why I like to work with roboticists rather than being one, because it shields me from a lot of those frustrations. Sample complexity is a huge issue in reinforcement learning, and that issue becomes especially apparent with robotics. So you want to train an agent to play Atari. You might be disappointed with how many samples it takes using current algorithms. But at the end of the day, all that really took was some simulation time. It's just computational resources. But you want to learn to train a physical robot using reinforcement learning, then the sample complexity issues are fatal. It's just impossible to generate enough data to learn. So there's a huge need for reinforcement learning algorithms that can learn with orders of magnitude fewer samples than the algorithms we have right now.
So, what does the end goal look like to you for reinforcement learning? And is it human level intelligence, or I mean, I know you've talked about the anthropomorphic fallacy, where you say that we ascribe to we think of intelligence as only human level intelligence. So, what other kinds of intelligence can you think of when attributing it to an agent or a robot?
Yeah, so I'm always wary of terms like human level intelligence. So you mentioned this anthropomorphic fallacy. I think we do have to be careful about thinking that whatever intelligence we build will be like humans in some way. And so the human level already kind of, I think, invites that misconception. Um, Also, just intelligence itself is one of these things that's very difficult to define, and these debates pop up from time to time among my colleagues on Twitter and at conferences about what do we mean by intelligence, how do we define human level intelligence, et cetera, et cetera. I always try to avoid these discussions because I don't find them very productive. I think you can waste a lot of time kind of chasing your tail trying to define things that resist definition. And I don't think it matters that much because I think how we define or don't define intelligence doesn't have a big effect on our research agenda right now. Basically, the short-term problems are really clear. We know what the obstacles are to progress now, and if we knew what the obstacles were going to be 15 years from now, maybe that would affect the prioritization we do now. But our ability to make predictions in AI is so limited. I always say that making predictions about AI more than 5 years in the future is a fool's errand. We just have no idea what's going to happen, how long it's going to take, what's going to work, what isn't going to work. And anyone who says that they know, they're fooling you or they're fooling themselves or both. So I think we know what the short-term problems are, and we have basically no ability to predict long-term. So it isn't that really that helpful to try to do so. That said, I think personally, I'm more interested in augmented intelligence than human level intelligence. The way I see it, it's like we already have human level intelligence, it's humans. So recreating that is not that interesting to me. What is very interesting is augmenting human intelligence. And that from the very beginning was a key motivation for me to get into AI, was just the feeling that a lot of the intractable problems that we want to solve, whether they're problems in science, like we're trying to come up with a unifying theory of physics, or political, social, economic problems. A big issue there is just that our brains are too small. We're just not smart enough to handle the complexity. So if we want to make progress on those problems, we need to make our brains better, and we can do that by augmenting them with intelligence that we develop on computers. So it's not so much like the human is here, and then the AI is like a totally separate entity that's down here but is gradually going up here. I think that's kind of the wrong way to think about it. I think it's more like we're building a single cognitive unit, and that cognitive unit consists of a human brain together with a computer. They're becoming more and more coupled, both physically and conceptually. You already have an iPhone in your pocket all the time. Sometimes in the future you'll have like something like Google Glass. Then maybe you'll have a computer chip in your brain. But it almost doesn't even matter physically how close they are, because cognitively they're already becoming one unit. And the question is, how can we improve that unit and harness it to solve some of these intractable problems?
So, what do you find most fascinating and satisfying about the research that you do?
So, as I said at the beginning, I think my love for computer science is based on the fact that fundamentally it's about creative problem solving. And I just find that so interesting. It's so open-ended because you're trying to build new tools, and so there's kind of no end to how you can do that. You're not like studying some physical properties of the universe that are kind of like static, and once you figure them out, it's over. You're trying to build better tools, so it's an open-ended creative process. Machine learning is, I think, particularly attractive from that perspective because it's really wide open. It's a very young field, so there are so many possibilities, and many of those possibilities have huge potential impact. And I think I'm quite lucky to just be in the right place at the right time. There's a revolution happening in the field, and I just happen to have chosen the field where all these exciting things are happening. Partly because of that, because there is so much buzz about the field, there's a huge amount of talent pouring in. So I have the luxury of getting to work with really brilliant colleagues and students, because so many smart people want to work on machine learning. So that I think makes the research quite rewarding. And as a professor, I have kind of like a mentoring role. So I think one of the most satisfying aspects of my job is getting to mentor like really high potential people, and to watch them thrive, and to feel like in some very small way I help contribute to their success.
Great. Sir, I was watching your the RL workshops at the Machine Learning Summer School in Moscow. So thank you for those 3 beautiful workshops. And so one thing you mentioned in the first workshop was that the more studies RL, the more it seems to look like the whole world is an RL problem, and which is just trying to maximize utility in the face of uncertainty. And you also mentioned about the reward hypothesis. So I'm curious to know if you think about RL in such a philosophical backdrop.
So, I mean, certainly I tend to view the world and in particular decision-making through a reinforcement learning lens. Reinforcement learning is about decision-making under uncertainty. And if you go out into the world, that's what that's what you're doing all day long. So, when I have to make, when I have to make decisions, I find myself thinking about it in that way. Like, okay, what's the expected return, and how do I reason about my uncertainty about it, and so on. So I kind of can't help but take that perspective on things, because it's the way my mind has been shaped by working on this topic for so long. But actually, I don't really think of reinforcement learning as something philosophical. I think of it as something really pragmatic. I view it as like a way to model the world so that we can solve practical problems. And it's a really useful model because it has a lot of strengths in this respect. It captures a lot of these key elements of you have to make decision making, you have to make decisions, you face uncertainty, you want to reason about expected payoffs. All of these things are captured there, and that makes it a really useful model, a pragmatic model for for solving these kind of problems in your actual life. But the kind of the key weakness of reinforcement learning is that it requires this reward function. And when you try to apply reinforcement learning to the real world, you're often confronted quite quickly with that weakness. So in that sense, it's often quite a poor fit, because it assumes you already are able to define this reward function when you go out there in the world and be like, wait a second, what actually is my reward function? What are my priorities? Am I actually able to quantify them? Do I understand myself well enough to say what my reward function is? Is it even consistent across time, or will I apply different priorities tomorrow than I will today? And I think the same is true of the reward hypothesis. So, the reward hypothesis says everything that we think of about goals and intentions can be well thought of in terms of, like a scalar reward function. And I think the really important word in that reward hypothesis is well. So if you take out the word well, then I think it becomes much more of a philosophical claim. But it's kind of like a trivial or tautological claim, because you're really just saying, if an agent has acted in some way, then post hoc, you can imagine that there was some value function for which the selected action was the maximal one, which is kind of obvious. So it becomes interesting when you put that word back in, when you say, okay, it's not just a characterization, it's a good characterization. And then it becomes quite, I think, a controversial claim, but not for philosophical reasons, for pragmatic reasons. Because the question becomes, pragmatically speaking, what is a good model for the kind of problems that we want to solve, for the decision-making that we need to do? And I wouldn't be working on reinforcement learning if I didn't think it was a good model. But it's not a silver bullet. It's not a panacea. It's not an infallible model, primarily because it assumes access to this reward function. So there are cases where you aren't able to quantify that reward function, so you aren't able to do reinforcement.
Implicit knowledge in our brain, and you cannot always quantify that.
Yes.
Yeah.
So that's a situation where learning from demonstration is often a preferable approach. So I mentioned already, the Teresa robot. You're not going to be able to write down the reward function for socially normative behavior at a cocktail party, but you can easily get demonstrations of it. So there's a different framework there, which is much more practical in that setting than reinforcement learning. Or, another situation is you do know the rewards, but they aren't really scalar. You have a number of different objectives. You have a multi-objective setting. And while in principle, you could always collapse those multiple objectives down to a single one, that's something we call scalarization. Doing so requires you to assign some priorities to the different objectives, which you may not be able to do, or you may not be able to do it at the time at which you need to do the learning. So, a multi-objective reinforcement learning, which is a topic I've worked on in the past. So, there's a whole family of algorithms there that don't fit that framework because sometimes that framework is not right. Or another example is, maybe the reward function and the reward function is scalar, but you aren't interested in maximizing just an expected sum of it. You might be risk sensitive. You might worry about the variance of the returns because, you're an investor and you want to be risk averse when you, bet on the stock market, or you even need to be risk seeking because you're in a situation where you need to do something quite risky and dangerous because it's the only hope of success. So, yeah, I would say the reward hypothesis is controversial, but for pragmatic reasons, not philosophical ones.
Right. So, how do you keep track of the overwhelming amount of research that's been going on? I mean, with deep learning coming in, there are a lot of papers being published every day on our site. So, how do you sort of manage that knowledge or keep yourself updated with the new things?
I think the short answer is that I don't. Because it's become completely hopeless. So for a while, my strategy was to try to focus more narrowly, which is already quite. It's a dangerous strategy because a lot of things happen outside of that narrow focus that are quite important to know about. But even within that narrow focus, it's become impossible. Even if I say I'm only going to read papers on cooperative multi-agent RL, even then there'd be more papers than I have time to read. So yeah, that ends up not being an effective solution. I quite like survey papers and tutorials because they can synthesize a whole area and give you the big picture view, while omitting the details that might not be necessary for you if you aren't going to be a practitioner in that subfield. So I think more people are working on developing tutorials and accessible material and surveys. But because of the sort of fire hose of papers that are being written, but there aren't enough of them. I think more people need to do that. Also, I quite like reading groups. So we have a reading group both at Waymo and in my academic lab because they force you to kind of weekly read papers and discuss them with other people, and that helps to stay on top of the literature, even though you're reading only a tiny fraction of what's coming out. I learn a lot from my students because my students will select some sort of sub area to focus on, and then they'll do a deep dive on it, and then they will sort of report back to me, as synthesized for me, what they've learned about those sub areas. So I rely on my students a lot to sort of teach me salient concepts that are going on in related subfields that I don't have time to read all the papers about. So you do what you can, but it's completely overwhelming.
Right. So that's the last question before we close. Do you have any advice for people who are starting out with reinforcement learning?
I guess I would say start with the basics. Before you can do machine learning, you need a really good foundation in calculus, linear algebra, probability, and statistics. If you don't feel comfortable with those, I wouldn't even start with machine learning until you do feel comfortable. And then similarly, you need a good foundation in machine learning before you can do reinforcement learning. You need to understand supervised learning and nowadays even unsupervised learning before you can do reinforcement learning. And also, I think within reinforcement learning, it's also really important to master the core concepts. So I think a mistake that a lot of people make is they sort of start with DQN, whereas they should start with the Sutton and Bartow textbook and learning about tabular methods. The empirical success of reinforcement learning may be quite recent, but actually the algorithms are quite mature. And the core concepts and the theory is really well developed, and an understanding of that, there's just no substitute for a good understanding of that foundational stuff. I guess I would also say it's really important to be realistic about what reinforcement learning is and what it can achieve. Essentially, it's like a promising but still largely unproven technology. And even in the best case scenario, it will be useful for only some situations. It's not going to be a panacea. I always tell people reinforcement learning is the tool of last resort, because reinforcement learning is learning through trial and error. And trial and error is the hardest and least efficient way to learn. So if you can learn any other way, if you can learn from demonstration, if you can do supervised learning, if you have any other option, you should do it. Reinforcement learning is what you should do when none of those options work. So I think it's important to sort of keep its limitations and scope in mind.
All right. Thank you so much, sir. Thanks a lot for sharing your insights on the field and for sharing your journey on this interview. Thank you so much.
Yeah, my pleasure. Thank you for having me.